Hello, Augies Worldwide. I'm Dave Kassler, amateur radio call sign KE0OG, here with episode number 290 of Ask Dave. Today I'm going to show you some charts that I showed recently to the Rochester Amateur Radio Association, or RaRa, that's in Rochester, New York, right on the shores of one of the Great Lakes. They asked me to speak, of all things, on noise. So I did. I said, how long do you want this presentation to be? They said, 60 to 90 minutes. Well, it did take a long time, but I've trimmed this down a little bit. I've divided it into two videos, 290 and 291. It's going to be, the first half will be about noise, and then the second half, which will be in the next video, which will be what you can do about the noise, if anything. Hopefully you can do more than nothing. So let's dive into the charts and take a look at what I said, and then we'll wrap up at the halfway point when we're done with these charts today. I gave this presentation on the 3rd of June to the Rochester Amateur Radio Association, commonly called RaRa, at their general meeting via a web conference. The subject is noise, just noise of all kinds, where it comes from, if there's anything you can do about it. I'm going to divide this YouTube video into two parts, and we'll follow the outline in this manner. In Ask Dave 290, we'll talk about natural noise sources, man-made noise, and ham radio-generated noise. And then in video 291, we'll talk a bit about receivers and about noise mitigation strategies. So what is noise? Well, it's what you don't want. If you want it, it's a signal. If you don't want it, it's noise. It's like the definition of weeds in your gardens. If you want it, it's a plant. If you don't, it's a weed. Now, we've got to keep in mind that one man's noise is another man's signal. For example, radio astronomy, looking at cosmic background radiation, things like that, that just sound like noise but are very important noise sources. Also, severe storm tracking can be done via lightning triangulation, and spread spectrum can sound just like noise too. Let's talk about lightning. It's always happening somewhere in the world. It's stronger in summertime in our northern hemisphere. And in the months of June, July, August, September, and so on, we can have some very strong lightning. Ionospheric propagation will carry this noise worldwide. Now, lightning is a spark, and it is a massive amount of energy released, and it's released by causing the air to become luminous. The air gets so hot it becomes luminous. It's black body radiation. It's the air. It's just gotten so hot that it will incandesce, and it puts out radiation at many frequencies, all the way up into light and beyond. And so it creates noise, and the ionosphere will carry the HF part of that noise worldwide. It's very broadband noise. It creates static, sometimes called atmospherics. Now we have a Q code that specifically refers to static, which is primarily from lightning. QRN, Quebec Romeo Nancy, refers to static. Now static you'll see on a pan adapter display as raising the entire noise floor across the band all together. That's often lightning that's doing that. I do note, kind of as an aside here, that if lightning hits your station, there is also serious acoustic noise. And I know that from experience, having been in my home when my station took a direct strike. Like I said, lightning is tracked all over the world. This happens to be from a week or so ago, lightning off the Gulf Coast, off of New Orleans. and the light-colored strikes have just happened, and they fade away gradually to red, and you can see the motion and direction of the storm that is carrying them. This is publicly available information. Just look up lightning maps on the internet. Let's talk about the sun also as a noise source. It is also a black body noise emitter. The surface of the sun is 5,000 Kelvin, 5,050 Kelvin, 5,500 Kelvin, depending on which book you look at. But the surface of the sun is glowing because it is hot. And it is glowing such that it incandesces. We perceive it as white light because we're used to looking at our own sun. But it also produces noise in the radio spectrum. You can even boresight your beam at dawn or dusk by pointing it at the sun. By the way, this is a good way to find out how high your beam angle is by following the sun from the time it rises and just following it across the sky. Your pointing will have to be very good to get it to the right angle at the right time, but you can determine how high your beam width actually exits the beam. Now, geomagnetic storm is something that happens around Earth, okay? It has to do with Earth. It can be caused by solar phenomena such as coronal mass ejection. The sun is constantly shedding matter, and that matter blows away from the sun at a very high rate of speed. It takes 2 or 3 days to get to Earth, whereas light takes about 8 minutes, but it's still moving at a phenomenally fast speed. The Earth is protected from this by its magnetic field, but the way magnetic fields work, this stuff, various protons, all this kind of stuff, come in along the magnetic field lines and hit the Earth in the polar areas. Now, it also excites the geomagnetic field around the Earth, gives it lots of energy, and it can completely black out HF propagation. The only good part about that, I guess, is that it creates some pretty wild aurora. Now, it can black out HF for a couple days, 3 days maybe even. But as it comes out of the blackout, the ionosphere is still very excited. And so it can offer some phenomenal propagation for a few hours right after the radio blackout ends. Sunspots, of course, enhance ionospheric propagation. We are at the low right now in the sunspot cycle, the very low. There's argument over whether we've even started the new cycle yet. Cycles last on average 11 years, but any given cycle can last 11 to 15, somewhere in there. I mean, it's a pretty broad range. Now, I want to talk about thermal noise. We're going to go to the opposite spectrum from massive objects like the sun down to submicroscopic objects like atoms and so on. Heat, the very definition of heat, it's energy, okay? And the way it manifests itself in matter is it causes the molecules in a piece of matter to whittle, and can cause electrons to move, and some electrons escape from their particular atom to create an electric current. After all, an electric current is movement of electrons or ions. And the heat that causes this, the higher the heat, the more of this thermal noise you get. The thermal noise is extraordinarily broadband and is seen as it's linear with the temperature. As the temperature goes up, the amount of thermal noise goes up. Now, electrons are both waves and particles. So as particles, they can create shot noise. It's just a little bing like that, whereas the thermal noise is like white noise. Most of this happens at very, very low levels. It's not a factor on HF, except possibly on like 12 or 10 meters, something like that. Now, thermal noise is white noise. The amount of noise energy that your receiver captures depends on its bandwidth. The noise, in fact, is given as dBm, which is a noise relative to a milliwatt, slash hertz, per hertz. So if you double the bandwidth, you double the amount of noise you capture. Shot noise is a very short noise spike, and hence broadband too. Another kind of noise that used to really create havoc in the ham bands was ignition noise. This is ignition in motors as they go by. The ignition noise used to be a real impediment to HF communications. Noise blankers were invented to deal specifically with this type of noise, and that's what noise blankers are good for, is ignition noise. Which is why you've got your nice modern HF rig and you turn the noise blanker on and you turn it off and you don't hear any difference. That's because what it was designed for has largely gone away. Modern ignition lines are high resistance plus better design, like electronic ignition, have greatly reduced ignition noise. It's getting rare. It's very rare that you hear it. If an antique car is going by, you might see it. Motors with brushes can cause similar noise. It's repetitive. Most motors these days are brushless, however, so you don't see that very much. Ignition noise used to be a real issue, and now it's not, but radios all still have noise blankers. The noise blankers sometimes on newer radios are modified so that they'll work with different kinds of noise, as I'll mention in a moment. Let's talk about noise from power lines. There's two major types, sparks and corona discharge. Now, both are broadband noise sources. I'm going to show you a picture of corona discharge in a second. Recall that high voltage as well as RF tends to travel on the surface of a conductor. If there is a sharp point on a surface, that high voltage, the electrons will leave and go into the atmosphere. This can cause significant line losses for the utility. And so they're interested. It's strongly affected by the physical geometry of the lines, sharp points, sharp turns in wires, and can be mitigated by certain devices that utilities can attach to the lines. Funny looking little things up there. It's also strongly dependent on weather, like humidity and wetness and so on. It can be very difficult to deal with because even though it's in the utility's best interest to fix it, the problem can be widespread and intermittent. It depends entirely on that particular utility's management philosophy on maintenance. Now, there are handheld, by the way, they are required to fix it if it comes right down to that. The Public Utility Commission in your state will require that they fix these things. There are handheld antennas and tools that can be used to track these down. Now, MFJ makes a few, some that track it down electronically, some that track it down acoustically. Now, some utilities, as I mentioned, are far more accommodating than others regarding getting these fixed. One other thing that happens with power lines is broadband over power line. Even if it's not something they offer to the public, it can be used internally. For switching reasons, remote control and so on. It's supposed to notch out ham bands, and I guess more and more people are doing that because broadband over power line, or BPL, seems to be fading as an issue. Now, I told you I'd show you corona. The actual picture is on the left. Depending on how much light is incident on your screen, you should be able to see lots of spots on this high voltage area here. Now, that's on a device that's supposed to be preventing corona discharge, but in fact is creating it at this point. It's the purple bright spots, and that you're looking at current just flowing into the air. because it's such high voltage. I put it as a negative on the other side. The magenta shows up here as green. Just you might give you a little bit better view of what's going on. Another source of noise are foreign broadcast stations. This is particularly a problem on the 40-meter band, and I remember when I was a novice that I struggled with these foreign shortwave broadcasts. There were so doggone many of them. It's better now because shortwave broadcasting as a whole has faded as an information dissemination technique because the internet has taken its place. We are in the International Telecommunications Union Region 2. And our 40-meter band is 7 to 7.3. But in regions 1 and 3, often, not always, 40 meters is 7 to 7.1 megahertz, and 7.1 to 7.3 is often allocated to shortwave broadcasting. Now, in the past, the broadcasters have been able to say, well, look, I'm not in region 2, I'm not aiming at region 2, it's not my problem. And that is still the attitude for a lot of people who still do use that frequency. It's less of a problem now than it used to be, but part of that, of course, is the sunspot cycle is so bad right at the moment. Now, the thing that usually gets you on a foreign shortwave broadcast is that carrier. The carrier is very strong, sometimes even megawatts are transmitted. Your receiver's automatic notch or use of a manual notch can help get rid of that nasty carrier. Another thing that's been in the news and ham radio on and off for the past 20 or 30 years is what's called over-the-horizon radar. Radar is a mechanism where you send out a pulse and you wait to hear the echo of the pulse. And the pulse might be off of an airplane or something like that. Radar is used extensively, of course, in many applications, but it usually uses microwave frequencies. However, over-the-horizon radar makes use of the ionosphere. These are put together by major military powers. I say that because they're extraordinarily expensive. They're used to seek out ships and aircraft at very long distances, such as out over the ocean. It uses pulses at HF with very sharply defined edges so that they can get maximum precision. The problem with a sharply defined edge is that it creates all kinds of noise on the shortwave band. This can obliterate a ham band. There's just this clackety, clackety, clackety noise. Now, noise blankers can be of some help here, perhaps. Note that today's radios have multiple types of noise blankers. For example, my Yaesu FTDX 3000 has a noise blanker wide, or NBW, that completely eliminates the newer Chinese radars. I was listening to them, you push the button and poof, they're gone. And push the button again, they're back. Now, Americans and the Russians have these over-the-horizon radars too. And so you'll hear strange things. It's not as common as it was. For a while, they had these things on constantly. And now they seem to be quite intermittent. This is interference. Quebec Romeo Mike. QRM is usually intermittent, but as I said, it can be as wide as an entire band. Let's talk about switching power supplies. This has become a real problem for ham radio. Switching power supplies are power supplies that instead of using a massive transformer and then a full wave rectifier followed by filtering, actually do their switching on and off through an entirely different technique. They do it at about 50 to 100 kilohertz, and that way they can use very small transformers. They're very common. They're in everything, even light bulbs and LED fixtures, such as grow lights and so on. They're much lighter and less expensive than the traditional transformer followed by a regulator-based supplies. But the switching transients, because they are square wave, can go well into the HF ham bands because a square wave has many harmonics, as I'll show you in a minute. Now, switching power supplies for ham radio are usually well filtered, but this is not necessarily true for switching power supplies that aren't for ham radio, such as computer power supplies, which are switching power supplies. The noise is seen on a waterfall display as periodic, meaning about every 50 to 100 kilohertz. It's usually ill-defined noise. It's not just a line, but it's a kind of a broad band. And these different bands are separated by the switching frequency. You can put ferrite beads on switching power supply inputs and outputs, which can be helpful because the emissions that come from these are conducted out the output lines and back over the input lines. I remind you that grounding is important. Grounding can keep your ham equipment grounded to central point ground and then to a ground rod right outside your shack, and can really help to reduce the induced noise from these emitters. Now, electric fences, which can also have loose connections that spark, are also pulsed. Even these invisible dog fences look like that. Now, the thing about switching power supplies using square waves, let me just show you a square wave here. This one, it goes from 0 to 1, so there is a DC component, which is at a half, because you see that there. The DC is at a half. The first harmonic, which isn't a harmonic, that's the fundamental, is this one right here. But now I want you to notice that the harmonics from a switch are on the odd harmonics only, okay? But what's important is that the power in these does not trend down to 0. There can be substantial power in a harmonic way, way up into the radio bands, even if this is a very sharp power supply at a lower frequency. So if you've ever watched the Fourier analysis of how a square wave is done, it takes an infinite number of harmonics to keep those corners sharp. And keeping those corners sharp really makes a difference. Now, there are other forms of square wave noise too. Computers, handheld devices, power cubes, home routers, switches, hubs, and Wi-Fi. I actually still have a hub. Grow lights, some solar panels just put out DC, like the ones I have for my solar system. But some solar panels also, instead of just DC, they actually have a small inverter that inverts their output up to household supply voltage, 110, 120, so that it can be shipped back to the utility. And those inverting solar panels have square wave generators, and there have been some issues of noise with these things. It's been written up in QST. Oh, I want to talk about intermodulation. This is a big issue at VHF and UHF. And because there is very, very little noise on a standard VHF and UHF channel, usually just thermal noise, a VHF transmitter can be very, very sensitive. However, when a VHF transmitter, for example, a repeater, transmits a signal, a diode of convenience, remember diode is a nonlinear device and it can cause mixing. A diode of convenience can be a loose connection somewhere, and if you take several VHF transmitters and they mix together here, you can get really weird results, and they'll mix with other signals, and it can create an output that is right at the input frequency of a nearby repeater input. The net result is an unwanted signal at the input to a repeater. Now, the usual and very common method of avoiding this is to add the tone-coded squelch, a CTCSS or tone-coded squelch. If the repeater doesn't hear the tone, then just the fact that there's noisy signal on the carrier-operated relay is insufficient to open the repeater. And this method is time-honored, and it has been done for a long time. If you have trouble getting into a repeater, they may have instituted a tone code squelch, and you can usually look up the tone in the repeater handbook, put it into your radio, and you'll be in good shape. By the way, this works the other way too. If you've got a simplex buddy that you want to talk to, and it's on one of those frequency where there is often intermod, you can have your buddy transmit the tone-coded squelch and set up your radio so that it won't open the squelch unless it hears the tone in the incoming signal, and vice versa. So the best course is to find and fix whatever's acting as the diode. However, sometimes it can be extraordinarily difficult to actually find the thing. I want to talk a little bit about hams as noise sources. Sadly, they sometimes are. QRM, which is intentional or unintentional interference. I'm going to echo what Riley Hollingsworth, the former counsel for the FCC, says about this. He is also now currently the director of the League's Volunteer Monitor Program. He says every radio ever built has a big knob on it, and if you are having problems with QRM, turn the big knob. Let's change frequency, in other words. Now, people will say, but I've got a right to be there. I've got a QSO in progress. While that may be true, you have had QSOs interrupted for other reasons. For example, fading, which is a common one that can cause, the band just drops out on you, or there's noise or something like that. You've had QSOs cut short by those things, and you can have a QSO cut short by interference. It is received wisdom that you never acknowledge the interference, because that just makes the person causing it feel good. Now, there is always the problem that possibly the person who is creating the interference with you can maybe hear you but cannot hear the other guy, so he thinks the frequency is not in use. Other ways hams can be noise sources is key clicks due to too short a rise time on CW DITs. 3 or 4 milliseconds is probably a good rise time on those. Too short, and you start getting a clicking that can be heard quite a ways off your frequency. And again, that's the square wave problem. CW pulses are supposed to be shaped so they don't have sharp edges, so they don't take up too much bandwidth. By the way, you can go too far the other way too. You go 6 or 8 milliseconds on the rise time, and the code now starts to get mushy, because the brain has a little bit of a hard time telling when it starts and when it stops. Another form of ham-generated noise is splatter from overdriving an amplifier on either single sideband or AM. This can come on AM from modulating past 100%. I showed in a recent video that it is perfectly possible to do that. Most of the newer radios have automatic level controls that will keep you from overdriving the amplifier. But if you have so much mic gain that you are inducing the ALC to operate a lot, it's going to distort your signal. So it's noise just from your end. There's something called front-end fundamental overload, close by signals that are overwhelming the receiver front end. I had this problem when I was a novice. My HW16 is notoriously prone to front-end overload, and there was a novice in this about a mile away from me. And whenever he got on, he obliterated me. I figured out how to put a 20 dB attenuator in the line, which helped, but I tracked the guy down. As it turned out, he was a guy my age. I was just out of college. And we decided to practice our code by sending code to each other. And so we did. We did that for months until we both got up to about 18 words a minute. And then we went down to the FCC field office in Los Angeles. And from there, we took our test and passed them together. Another thing that you can do on digital, you can create the overmodulation or distortion by not using the linear part of the modulation transfer function in the rig. In other words, too much gain or from overdriving an amp. Most digital modes are QRP modes. They're really not designed for a lot of power because what happens is FT8 is so popular that there are too many people on the bands, and so people get frustrated and they put power behind their signal, and that just makes the situation worse. It's a classic case of the tragedy of the commons. If you look that up in a philosophy textbook, you'll see what's going on there. We've got this thing that we share, which is a certain amount of bandwidth, and there's too many people to share it, and so everybody tries to get more than their share, which creates just a mess, because then in the end nobody gets anything, and that is the tragedy of the commons. It comes from the common ground where people would graze their sheep. Another form of ham-induced noise sources are badly adjusted speech compression. Get your manual out, read it carefully, walk through the speech compression section, and set your speech compression to exactly follow those instructions. That is your best speech compression. It will seem less than you might otherwise want to do it. Now, speech compression can allow your signal as much as a 50 to 100% gain in understandability at the other end by adjusting the midtones and so on. It can be a very valuable tool, but overdone, like anything, is not a good thing to do. Also, and I've noticed this too much, and I think a lot of people notice it because now they have radios that you can look at the audio spectrum of the person who is talking to you, and you get some weird frequency responses of microphones that can create either muffled or tinny sound. I ran into this problem with a microphone from Tentec, their 777 microphone, which was a copy of a Heil Pro 6. And I didn't realize it, but it was a very muffled tone. And I was wondering why I wasn't getting a lot of CQ responses on my old Tentec. And when I got the Yaesu, I discovered by looking at my transmitted spectrum that it was very muffled. So I used the features inside the radio, and a lot of radios have this these days, where you can adjust the bass, the treble and the mid frequencies to get them nicely flat so that you have a very good sounding signal on the air. And I consider any distortion of a signal to be the equivalent of adding noise to a good signal. So let's not add it right on transmit. Well, that's probably more than you ever wanted to learn about noise, but there's lots of noise stuff out there. The study of noise is actually very interesting, and I had the opportunity as part of my graduate studies in electrical engineering to study more about it. It can be very complicated mathematically, and it's very interesting. It's how the world works, really. The world is full of noise, and when you get right down to it, everything is kind of noisy. But mankind fights against that and tries to bring some order out of all of this noise, and generally does pretty well. So the next video, Ask Dave 291, will be the second half of this, which talks about receivers and what you can do about noise. So stay tuned. In the meantime, please take a look at www.dcasler.com/support for different ways that you can support this channel. And until we next meet, 73.